All right, here we go, guys. This is the Unit 2 review. The Unit 2 review. So the test is just around the corner, and this is to help you get prepared. This is everything kind of all together in one neat little package. So let's go ahead and get rolling with this. We are first asked to use the graph to find the limit if it exists. If the limit doesn't exist, explain why. All right, so using the graph. So when x, the first one is as x goes to 0. And so just looking at that, that is going to be equal to 4 right there. Because again, if this is where x is equal to 0, what does the line to the left and to the right both point at? They both point at the value of 4. Next, we are looking at the limit as x goes to -1. And again, both of the arrows do point to the same thing, and that should be the value of 5. Find the limit. Okay, so here, the majority of limit finding is just really basically substitution. It's really nothing more than that. If there is illegal mathematics somewhere, then you probably need to, factor or something like that. But for the most part, it's just basic substitution. Nothing too crazy. All right, so here is an example of what I mean. So you'll notice that this denominator becomes a 0. There's illegal mathematics in here. So you can't let that go. So what we need to do instead is, this is most likely you need to factor something. So I see that this, we didn't take the limit yet, we're just changing the problem. The denominator is t plus 2 minus 2. With the numerator as t plus 2. So I saw that there was illegal mathematics. So as I said, chances are the problem is most likely factorable. All right, so this is a 1 over -4, or -1/4. All right, so we have some illegal mathematics here. With the numerator being a square root and a number, most likely we're going to be multiplying by the conjugate of the numerator. So this is going to be x minus 3 plus 1. So that is what we're multiplying both the numerator and the denominator. And it should probably come out to be something decent. So the squaring, this is just of the numerator. The square roots go away, so that leaves an x minus 3. It'll be a positive square root and a negative square root, so that goes away as well. And then a -1 with the -1 times 1. And the bottom, again, most likely that chunk right there, the x minus 4, is most likely going to drop from the problem. All right, so I see that indeed the numerator is an x minus 4. So that drops. So that leaves us with the limit as x goes to 4, x minus 3 rooted plus 1, all as a denominator. Here I can plug in the 4. So 4 minus 3 is 1. Square root of 1 is 1. 1 plus 1 is 2. Last but not least, sine of 0 of, okay. Let's see if I just kind of play around with some trig identities. So this is 1 over sine minus cosine over sine. All right, so this is going to be the limit as x goes to 0, 1 over sine minus cotangent. I'll get back to this one. I'm not exactly sure what the problem is. Let me. Sorry. Number was that? That number was number 23. The book has it as equal to 0. Yeah, I'll get back to you on that one. I'm not exactly sure what the deal is with that one. I'll come back to this one. I'll put it in the comments or something. All right. Okay, back to the lecture at hand. All right, so limit of c, and there's a multiplication. That implies that the limit is still existent in the multiplication itself. So what I'm referring to is, this is how you can see the problem right here. So this is just the limit of x goes to c of f times the limit of the x goes to c of g. And so what that would be is -6 times 1/2. Same with this. So this is the limit as x goes to c of f of x. The addition, and you also take out the 2. So an inside constant, a multiple of a constant, becomes a multiple on the outside. So again, this is -6 plus 2 times 1/2. So 2 times 1/2 is 1. So the multiplication takes place before the addition. So this is -6 plus 1. This is -5. Use a graphing utility to estimate the limit. Use a table to reinforce your conclusion. Then find the limit by analytic methods. Use a graphing utility and estimate the limit. Okay, so graphing utility to estimate the limit. So I'm going to put it into the y is equal to the square root of 2x plus 9 minus 3. I'm going to put the entire numerator in its own parentheses. So that's the numerator, and then it's divided by x. And I'm checking this right around 0. So what I'm going to do is I'm going to ask it, what is it when it's really, really close to 0? Like 0.0001 and -0.0001, something like that. And it's coming out to be 0.0003. So the answer should be 1/3. Okay, so graphical, that answer should be 1/3. Test it with analytic methods. Okay. Okay, so they want me to create a table, actually. So in essence, what I'm doing is I'm guessing a number that is real close to the limit. So I'm guessing what the heck is 0 by guessing numbers that are wicked close to 0. That's in essence what I'm doing. And so this came out with 0.33333. This came out with 0.33334. That sort of idea. So you can kind of guesstimate that the middle ground should be 1/3. Okay, test the limit if it exists, and so 3, so this is a 6. That's not a big deal. 4, I don't know if this exists. And just for giggles, this is what I'm going to try. I'm going to try a square root plus 2. So let's give it a go here. So square root x, positive 2, negative 2, and then that comes out to be a -4 as the negative 2 multiplies the 2. And then, well, you know, it does kind of work out. So that drops, and now the limit as it goes to 4, so that's 2 plus 2 is 4. The limit as x goes to 2. All right, so what I'm going to do is I'm going to find the limit as x goes to 2 from the negative. So 2 from the negative would be where the x is less than 2. That would be this top equation right here. So again, I'm going to plug in 2, and that's 0. And then I'm going to test where it is the limit when x goes to 2 from the positive. And that means when it's bigger than the 2. Okay, so it's that bottom equation right there. And so that'll be 2 minus 2, 0. What I notice is the limit left and limit right are both the same. That implies that the limit itself is indeed equal to 0. So limit left is equal to the limit right. Those answers would have been anything different than each other, then the limit itself does not exist. Removable, non-removable discontinuities are the values which f is not continuous, which the discontinuities are removable. So here we have an x, which is an x squared minus 1, which is the same thing as an x plus 1 minus 1. I see that the x drops, and so that means the removable would be when x is equal to 0. The non-removable, so the non-removable, the other discontinuities, whatever they happen to be, would be x is equal to -1 and x is equal to positive. Yeah, so it's discontinuous for all 3 of them. It's discontinuous for 0, -1, and +1. And the only one that's a quote-unquote removable discontinuity is the x is equal to 0. Okay, where is this function continuous? this is all good. There is no illegal mathematics. So x is good for all real numbers. It's all good. Negative infinity to infinity is the domain. Okay. And again, what I'm looking for this, like where is it continuous? I'm looking for illegal mathematics. And so what I'm noticing on number 53, this has to be greater than or equal to 0. The inside has to be greater than or equal to 0. You can't have a square root of a negative. So that has to be greater than or equal to 0. Not necessarily x, I'm sorry, I misspoke that. But the inside has to be greater than or equal to 0. So that means x has to be greater than or equal to 4. So that would be 4 to infinity. Use the intermediate value theorem again. The idea of an intermediate value theorem is if it is continuous, then there will be, sorry, let me kind of make this a little bit more extreme. If this is continuous and this has like, you know, like a height of 5 and a height of 2 or something like that, that means there is a value somewhere in between these two things where all values from 2 to 5 are represented. Like there's a value when it's 3, there's a value when it's 4, there's everything in between 2 and 5 is somewhere in between the two. That's the intermediate value theorem. There's an intermediate inside value. Okay, so we see that the value is continuous. Okay, we see that it's continuous. Now what we want to do is show that there is a 0 in between here. All right, well, to do that, what we do is we show those endpoints. All right, so we show what are these values. Okay, that's what we're showing first and foremost. What are those beginning and ending values? And that will show that there's going to be the value of 0 somewhere in between these two things. Okay, there's going to be a value of 0 somewhere in between these two things. So here we go. So a value of 1. So 1 to the third minus 3. 2 minus 3 is negative 1. And then we try the 2. So that's 2 to the third minus 3. So that's 8 minus 3. Excuse me, 16 minus 3. All right, so in essence, what we did is we showed that there is one endpoint that has a value of 13 and another endpoint that has a value of negative 1. So by the intermediate value theorem, the value of 0 has to be somewhere in between those two values. So yes. So I'm not exactly sure how to write this. So by intermediate value theorem, you know, f of 1 is less than or equal to 0, which is less than or equal to f of 2. Something like that. Okay, find the one-sided limit. Right, so before I get into my positive and negative zeros, which I'm assuming is where this is going, I do notice that this is factorable. Not that it really cancels anything, but it'll kind of help my mathematics out here a little bit. All right, so again, this this limit goes to 1 from the negative. So this is like 0.999 something something something. That's kind of what I have in my brain. So what happens to the denominator? If it's 0.99999 minus 1, that's a negative 0. That's a negative 0. Okay. negative 0 over some number. It doesn't really matter what number, but the 0 is on the bottom. That implies that this is, what is it, 2, 2, yeah, it would be 4. That would imply that this is a negative infinity. Oh, this technically would be an x. Ooh, get a cancellation here. So that's 1 minus 1 plus 1. This is equal to 1. All right, goes to 0. Okay, so I see a denominator of 0. That won't work. Okay, what I'm going to do is I'm going to put an x to the third on this side, so that means I need to multiply both top and bottom. So this is limit as x goes to 0 positive of x to the fourth minus 1 all over x to the third. Okay, so plugging in this type of 0, I see that this is, again, this is a small positive number. So this is going to be a positive 0 over negative 1. And so this should be a negative infinity. Negative divided by a positive. Or I guess I could have just told you that from the original problem. That would be 0 minus infinity. That's technically what it is. 0 minus infinity. Okay, find the limit as this goes to infinity. So again, I will get a common denominator. This is 8x plus 1 over x. So in this situation, when you have a limit that goes to infinity, you get to ignore all the things that don't have x's, and then you simplify. This is going to be equal to 8. Again, I could have probably told you that from this. This is going to be 8 plus 0. When you plug in the infinity, 8 plus 0. All right, because this thing goes to infinity, you get to eliminate anything that doesn't have an x, and then you simplify. Negative infinity, still the same idea. Eliminate anything that doesn't have an x, simplify. And so because this is, this would be negative infinity. And that's it. All right, kids, that is your review. Again, brush up on your factoring skills if you need those factoring skills, and kind of get in the habit of identifying like a positive and negative 0, like kind of like in problem number 69 here. Figure that out. And again, yeah, if I can come to a conclusion, I'm sure there's an easy way of me doing what problem was it? This problem down here. Actually, before I let you go, let me just try one random idea. One random idea. So this numerator is going to be 1 plus cosine minus cosine and then minus cosine. That's where it is right there, most likely. This is where, yeah, this is probably where everything comes to fruition here. All right, so yep, there is, I figured it out. All right, so if you recall that the idea that sine squared plus cosine squared is equal to 1, thus this is one of those trig identities. So if I subtract cosine squared from both sides, that means sine squared is equal to 1 minus cosine squared. That's exactly what that numerator is. So using the basic trig identity, I can replace this numerator with sine squared. Okay, so from here, what I get to do is I get to eliminate this sine with one of the sines, and now there's no illegal mathematics. I could absolutely plug in a 0, and it would totally be fine. So of my unit circle, when I go to 0, that's the 0.10, that's cosine sine. So plugging in that 0, the sine becomes a 0, so this is 0 divided by 1 plus the cosine, and so this is 0 divided by 2, which, long story short, is still 0. There you go. Figured it out. Now that's the end of the lesson.